Okay, so we're going to continue with solving differential equations. So this time we're going to be looking at the second type, which is the homogeneous differential equation. Okay, so type 1 we did earlier, that was the separable case. Now we're looking at type 2, which is the homogeneous case. Okay, so we're looking at the differential equations which have the same type as last time. So it was y prime. So first order differential equation where the right hand side was some function of x, so a single variable x, and the function y. So for the separable case, that right hand side could be split into g of x times h of y. Now we're looking at a different type where this function f can be written as a new function capital F, where it's a function of a single variable, so not f of x and y like above, but a function of y over x. Okay, so we treat y over x as a single variable, and we get this new function capital F. Okay, so how do we go about solving this differential equation? We're going to use a change of variables. Change of variables. Okay, so this inside variable for the capital F function y over x, we're going to call that u. Okay, so instead of using the variables y and x, we are now going to use the variables u and x. Okay, so a little bit of rearranging, we see that y is equal to u times x. Okay, so a little bit of rearranging. Now what we want to do is find y prime for that left-hand side. So we're going to do the derivative on both sides. So y prime is equal to, so u is a function of x, x is a function of x, so it's a product rule. So we're going to have u prime x plus, and then we leave the first one alone and then take the derivative of the second. So it's just plus u. Okay, so that means our left-hand side, the y prime, is replaced with u prime x plus u. Okay, and the right-hand side, capital F of y over x, that's just going to become capital F of u. Now, after this change of variables, the hope is that this new differential equation is easier than the original one. Sometimes that's not the case, but we try to hope that this new one is at least easier than the old one. Okay, so we hope this new one is easier than the old one. Okay, if that's not the case, maybe you're going to have to try something else. But a lot of the times, if you do see a homogeneous differential equation, this process will make it easier. Okay, so the idea is to solve this easier differential equation. For u of x. Okay, and then once we have u of x, we can get back to the y of x because we know y is equal to u of x times x. So whatever solution we get for u, we just multiply by x, and that gives us our y solution. So it will be x times u of x. Okay, and then that will be our y solution. Okay, let's have a look at some examples. Okay, so let's say we have y prime is equal to y squared plus xy over x squared. Okay. Now the idea is to take this first order nonlinear differential equation right? Because we've got a y squared, so immediately it's nonlinear, and convert it into something that's a lot easier to work with. Now, as it is, this is not really a function of y over x, right? We need something like this with the y over x. So we need to first simplify. So let's take the y squared and divide it by x squared as our first term. Plus, and then xy over x squared as our second term. Okay, so we're going to split up the fraction. Now, y squared over x squared, we can write as y over x, and then the whole thing squared. Then we have an x at the top, x squared at the bottom, so we're left with an x at the bottom, so we get y over x. And this will be our function capital F of y over x. So you see we have y over x squared plus y over x. That's going to be our capital F. So we're going to do that substitution with u now. So the left-hand side, instead of y prime, we're going to write u prime x plus u. That's going to stay on the left-hand side. And then on the right-hand side, instead of y over x, we're going to put u. Okay. Now, after all of this is done, we hope that this is much easier to solve than that nonlinear differential equation we had at the beginning. In fact, it is. So we got u on both sides. We can cancel that. So we get u prime x equals u squared. Now, at this stage, this is a separable differential equation. So we started with a type 2 problem, and now we go back to what we had earlier with separable. So there's going to be a lot of mixing between things. So you could start off with it being homogeneous, and then maybe you end up with something that is linear that you need to solve. Or you start off with something homogeneous, and it ends up becoming separable. Okay, so you can have the mixing of these techniques. Okay, so this is separable. So the u prime, we're going to write as du by dx. Okay. Now we need to make sure everything's on the right side. So on the left-hand side, we want that to be all of the u stuff. So the u squared, we're going to take over. Okay. Then the x that needs to go on the other side, and the dx that needs to go on the other side. And now we can integrate both sides, and we can put our plus c. Now this just becomes two integral problems. So the integral of 1 over u squared, that's like u to the minus 2, so it will be minus 1 over u. And then integral of 1 over x, that's just the natural log. And we have our plus c. Okay, now we need to solve for u, and once we have u, we can then get y. So let's take the minus over to the other side. So we have 1 over u is minus the natural log of x minus c. Then we need to have not 1 over u, we want u. So we can take the reciprocal. So 1 over all of this stuff. Okay, so that's our u function. Now we don't want u, we want y. So if we go back up a little bit here, y is going to be x times whatever we had for u. So finally, we can write down y of x. That will be x times what we have above. So that will be x over minus the natural log of x minus c. Okay, and again, it's a first order differential equation. So we're going to have one unknown somewhere there. If this was second order, you would have 2 unknowns. Yeah. Now, if some initial condition was given or some boundary value was given, then you could solve for c. But since nothing like that was given, we leave it as a general solution. Okay. So later, if I say y of 1 is 0 or something like that, then you could solve for c. Right. Any questions on this? All good. Okay. Let's have a look at another one. Okay, so we have y prime is equal to xy over x squared minus y squared. Okay, so again, first order differential equation, it's non-linear, right? We've got y at the top divided by some y squared at the bottom, so clearly non-linear. Is it separable? No. In the bottom, we've got x squared minus y squared. We can't, split that up into two parts. So the next thing is trying to see if we can make it look like something with y over x. So in this case, it's not. We've got x times y in the top and x squared minus y squared in the bottom. So it's not something with y over x. So what we can do is take the top and divide it by x squared, and then take the whole bottom part and divide it by x squared, so that this y squared divided by the x squared gives that y over x all squared that we need. Okay, so that's going to try help. Okay, so dividing top and the bottom, what do we get? Okay, so we're going to have some fraction at the top and some fractions at the bottom. So in the top, we're going to have x times y over x squared. Okay, so we'll simplify that later. And then in the bottom, we have both of those divided by x squared. Okay, so you should see what we're trying to do here. So in the top, we have x at the top, x squared at the bottom. We're going to have an x left over at the bottom. Okay, so we have y over x. That's good. That's what we need. X squared over x squared, that's just going to be a 1. And y squared over x squared, we can write that as y over x and then the whole thing squared. Okay, and now this is in the form that we want. So we have y prime is equal to all of this, and this is what we can write as capital F of y over x. So when we do that substitution with u, the top will be u and the bottom will be 1 minus u squared. Okay. So the y prime, we're going to replace with that expression with u. So it will be u prime x plus u. And then on the right side, the top, that's going to be u. The bottom, that will be 1 minus u squared. So we have something like this. Okay, now again, we look at this and we try and solve it. Again, this is a first order differential equation in u, and it is non-linear, right? We've got u over 1 minus u squared. So we're going to have to try to do some simplification. Let's take the u over to the other side and try and simplify that. So u over 1 minus u squared minus u. Okay, so the idea is hopefully we can simplify this to something that's easier to work with. Okay, so on the right-hand side, we have a fraction minus u. Let's try get the denominators the same so we can add the fractions together. So we're going to have u prime x is equal to u over 1 minus u squared minus. Now we want these two fractions to have the same denominator. So it's going to be u 1 minus u squared over 1 minus u squared. Okay. Now they have the same denominator. We can then combine them. So this will be u prime x is equal to, let's put all the top parts together. So it will be u minus u plus u cubed. Okay, that's just distributing the u inside there. Okay, all over in the denominator, that stays the same. There'll be 1 minus u squared. Okay, u minus u, that goes away. So we end up with u prime x is going to be u cubed over 1 minus u squared. Now, in this form, it is separable, like we saw earlier. So all of the u stuff we can take over to the left-hand side. All of the x stuff we can take over to the right-hand side. So we're going to have 1 minus u squared over u cubed du. And then all of the x stuff we take over to the right-hand side. That will be 1 over x dx. Yeah, so we've done the separation. Now on the left-hand side, we can integrate that. On the right-hand side, we can integrate that. And we can put our plus c. Okay, so we've got these two integral problems. Let's go through them one by one. So we're going to have 1 over u cubed. So that will be integral u to the minus 3. Then minus u squared over u cubed. You can have a u at the bottom. So minus 1 over u. Okay, on the other side, that stays the same. Okay, so integral u to the minus 3. We're going to have minus 1/2 1 over u squared. Then we're going to have the natural log of u. Then we're going to have the natural log of x plus c. Okay, so we have our expression for u. Now we want to go back to y. So remember, back up a little bit. Over there. So u is y of x. So we're just going to substitute that in now. Okay, so we're going to have minus 1/2 1 over y over x squared minus the natural log y over x is equal to the natural log of x plus c. Now, you could leave it like that. That's perfectly fine. If you want to simplify further, you can do that. But that's just some algebra. Okay, so simple algebra to simplify further. Okay, I'll leave that for homework, so you can try that out. Okay, any questions about this example? You're all good. Okay. And again, please note how we used the separable differential equations in both examples. So we started out seeing it was homogeneous, and then to solve for u, we then had to use the fact that the u differential equation was separable. So if we go back to what we had last time here, right? These four methods over here, it's not one at a time. It can be a mix. So we saw with these two examples, it was number 2. And then to solve it, we needed number 1. Okay. Then if we see something as number 3, maybe we need number 2 and then number 1. You might have to use all 3. Okay. So it's not one at a time things. It's always going to be some kind of mix of them. Okay. Any questions so far? All good. Okay, let's have a look at number 3, linear differential equations. Okay, so the first two cases, we saw that those examples were non-linear, right? We had fractions with y, we had y squared, and so on. That makes it non-linear. For case 3, we are only interested in cases where it is linear. Okay, so if you see something that is non-linear, ignore this third one. You cannot use it. If the differential equation is linear, you might be able to use 1 and 2, but you can also use 3. Okay, so please keep in mind it has to be linear. Okay, so we will solve first order linear differential equations using an integrating factor. Okay. So what do these first order linear differential equations look like? So we can write them out generally as y prime plus some function p of x times y is equal to q of x. Okay, this is the standard form. Right? It has to be linear, so there's no y squared or y cubed or tan of y or anything like that. If it's linear, it must just be y. And we know from last year that we can take this y and multiply it by some function. It's still linear, so we have p of x in the front there. And we can add some function. It's still linear, so we have q on that right-hand side. So this is the standard form for a first-order linear differential equation. Okay, so whenever you're working with these, it must always be in this form. If it is not in this form, for example, if p of x times y is on the right-hand side, it's going to mess up everything. Okay, it has to be in this form to use the method. Okay. So this comes with a proof. So we're going to show that any first-order differential equation that's linear can be solved using this integrating factor. Okay, so proof. Okay, please learn the proof. It can be tested. So first of all, we're going to show what this integrating factor is. And secondly, we're going to show that we can solve any of these equations using that integrating factor. Okay, so there's two parts to the proof. Okay, so firstly, the idea of the proof. So what do we actually want to do? Okay, so we want to write y prime plus p of x y, that left-hand side. We want to write this as the derivative of a product of two functions. Yeah. So instead of having y prime plus p of x times y, we want to write it as something like d by dx of f of x times g of x. We want to write it as a derivative of a product. So we need to find what these two functions are so that we can replace this y prime plus p of xy with this derivative of the product. Okay, to do this, we introduce a new function called the integrating factor. Okay, so this integrating factor in the textbook and notes online and so on, you'll see it as either mu of x, so Greek letter mu, or you'll see it as capital I of x. Okay, so you'll see it one of these two. Okay, you'll see. In the textbook, you see the first one. But if you're looking online, you might see that second one. Okay. So again, we want to write this left-hand side. Okay, this left-hand side here. We're going to write it as the derivative of a product. Okay, and the way we do that is by doing the derivative of mu of x times y of x. Okay, so those are our two functions. So we're going to take our function y, multiply it by this integrating factor function mu, and then we're going to take the derivative. Okay, so this is going to be equal to, we can use the product rule, derivative of the first one, we're going to leave the second one alone. plus, then we're going to leave the first one alone and then do the derivative of the second. Okay, so that's just using your normal product rule. Now, what we're going to do is compare this product with this left-hand side, that left-hand side there, multiplied by our integrating factor. So we're going to take our integrating factor, multiply it to that left-hand side, and then compare these two equations. Yeah, and we'll see they're going to be quite similar. So firstly, we're going to have mu times y prime. Plus, and then we're going to have mu of x times p times y. Okay, and we can see already with the two equations, we have these two terms equal. So in equation 1, I'll put that in pink, we've got this mu times y prime. And here we have mu times y prime. Okay, those are equal. Now, if these two equations are to be equal, the pink ones are already equal, it means the other two must also be equal. So let's put that in blue. Okay, so we've got two equations, 1 and 2, and we want these to be equal. So the derivative of the product, that's equation 1, and then the integrating factor times that left-hand side, that was equation 2. We want these to be the same, which means the two pink parts must be the same, and the two blue parts must be the same. Okay, therefore, in the first one, we're going to have mu prime times y from equation 1 must be equal to that blue part from equation 2. Okay, and this gives us our equation 3. Okay, so this comes from the fact that we want equation 1 to be equal to equation 2. That gives us equation 3. Now, on both sides of equation 3, we have y of x. Okay, on the left and the right, we can cancel that. Okay, that's going to get cancelled. So we end up with mu prime is equal to mu times p. Okay, so I'm going to leave out the mu of x and so on just to make it a bit simpler. So here we have a differential equation for mu. Okay, it's first order, it's linear. In fact, it is separable. Okay, so that right-hand side there is separable. Okay, so we end up with a first order separable differential equation for mu of x. Okay, so again, step 1 of the proof is to find this integrating factor. Step 2 is to show that it works for all of those equations. So we're almost done with step 1. So here we can write this as d mu by dx is equal to mu times p. Right, it's separable. We know what to do with those. We're going to take the mu to the one side. We're going to take the x to the other side. So we have d mu over mu is equal to p of x dx. Okay, and we're going to integrate both sides. Okay, so here we get the natural log of mu of x is equal to the integral of p of x dx. Okay, so we end up with that. Now we don't know what p is, so we're just going to leave it as an integral. And remember, we have our plus c. Okay, we've got the natural log of mu of x. We want to undo that. So exponential on both sides. We end up with mu of x is equal to some constant a, e to the integral p of x dx. Okay, that is our integrating factor. Okay, so step 1 is done. We've got our integrating factor. That's what it looks like. Now for step 2, we need to show that given this integrating factor, we can solve the differential equation. So step 1 is done. We have the integrating factor. Okay, now for step 2, we need to show it works. Okay, so how do we do that? Okay, so we go back to our differential equation and we try and see, does this integrating factor actually work? So we have y prime plus p of xy is equal to q of x. Right, that's what we wanted to try and solve. Now, if we go back a little bit, over here, remember, how did we get this integrating factor? We took that left-hand side of the differential equation and we multiplied by mu. Everyone see that? Okay, so that equation 2, we took the left-hand side and we multiplied by mu. We're going to do the same thing now. But remember, you can't just multiply one side, it has to be both sides. So we're going to take both sides and multiply it by mu of x. Okay. Now that left-hand side, we know what that is. If we go back again here. Okay, so we're looking at equation 2. We now have that left-hand side. But equation 1 and equation 2 are equal. We made them equal. So the left-hand side of equation 2 is equal to the left-hand side of equation 1. Right? Because we made them equal. That's how we solved for mu. So instead of the left-hand side of equation 2, we're going to put the left-hand side of equation 1 because they're the same. Okay, so this was left-hand side equation 2. We're going to replace that with the left-hand side of equation 1. So now this was the left-hand side of equation 1. And remember, we can do this because equation 1 is equal to equation 2. Okay, so now we want to solve this. Well, that's easy to do. We can just integrate both sides. So the integral of the derivative, that just goes away. So we have mu of x times y of x is equal to the integral of mu of x times q of x dx plus c. Right, you do your integral, you have to put your plus c. Now we want to solve for y, so let's take this mu over to the other side. So finally, y of x is going to be 1 over mu of x, the integral of mu of x times q of x plus c. And we're done. That's the solution. Okay, and that is the end of the proof. So given any first order linear differential equation, number 1, we can find an integrating factor. That's this mu. And once we have the integrating factor, that's the solution. So inside the integrating factor, we've got that p of x there, and we've got q of x inside there. Yeah, and that gives us our solution, y of x. Okay. Any questions on the proof? All good. Okay. Please make sure you go through that. It can and will be tested. Yeah. Yes. Over there. Yeah, so remember, if we go back to here, so we want to write that left-hand side of the differential equation as the derivative of a product. That was the goal. So that left-hand side of the differential equation, that's here, that's equation 2, multiplied by mu, right? Because it's f times g, you have to multiply by something. And we want to write that as the derivative of a product, that's equation 1. And we want those to be the same. So this is what we want to be equal. So we want the left-hand sides to be equal from here. Okay. Now, if the left-hand sides are equal, the right-hand sides are equal. We see the pink terms cancel. So that means the blue stuff must be equal. And if the blue stuff is equal, we get this differential equation to solve for. Okay. So it's just matching up the sides. So we want the left-hand sides to be equal. So that means the right-hand sides must be equal. Okay. Any other questions? Okay, so the main thing is this. Okay, we want that left-hand side of the differential equation to be written as this derivative of the product. So here, that's going to be this. Okay, so that's the right-hand side of the differential equation. We want to write it as the derivative of a product. So equation 1 and 2 must be equal. Okay. Any questions? Okay. Just go through that again in your own time. If you have any questions after that, come and see me. Okay. Let's have a look at an example. Okay. So we've got x, y prime plus y is equal to 3x squared. Okay, so immediately we can see that it is linear, right? Because it's just y by itself. It's not y squared or any function of y, so it's linear. It's first order because there's only y prime, so we can use an integrating factor. So this is linear and first order. So we can use an integrating factor. But it's not in standard form. Okay, so we need to fix that first. So let's write it in standard form. So it's going to be y prime plus 1 over x times y is equal to 3x. So this is the standard form. So y prime plus p of x y equals q of x. Okay. Remember, it must always be in standard form before you do anything else. Okay, so we've got p of x and we've got q of x. Okay, so like we did for step 1 of the proof, we need to find the integrating factor. And then like we did with step 2 of the proof, we write down the solution. So the integrating factor mu, that will be e to the integral p of x dx. So that's e to the integral 1 over x dx. That's e to the natural log of x. They cancel. So we just get x. Okay, so that's the integrating factor. Once we have the integrating factor, we can directly write out the solution. So y of x, this is going to be 1 over the integrating factor, the integral of the integrating factor times q, and then plus c. Yeah. So again, once we have the integrating factor, the solution is just substitute and integrate. So this is going to be 1 over x, the integral of x times q, that was 3x from the side there. And then plus c. So this will be 1 over x. Integral of 3x squared, that will just be x cubed, plus c. So finally, x cubed over x, that's just x squared, plus c over x. And that's it. Okay, so again, 2 steps. So step 1, find the integrating factor. Okay, so you've got that integral of p to do there. So you find your integrating factor, and then step 2, we just use that equation there to get y. Okay, that's it. So just 2 things to remember. That equation there for mu, the e to the integral p, and then that equation for y. Okay, that will not be given. You need to remember that. Okay. Any questions for this example? Okay. It's not so bad. Just substitutes and integrates. Okay, some homework problems. Okay, so these homework problems are just for the linear case. So we have y prime is equal to sec x plus y tan x. Okay, already it's not in that standard form. Okay, so remember it's y prime plus p of x times y equals q of x. That tan x, that needs to be on the other side. Okay, number 2, y prime plus 2y is equal to 4x. This is in standard form, and our p of x is just 2. And number 3, y prime times sine x minus y is equal to 0. Okay, so we have something like that. This is not in standard form. We need to first divide by the sine x. Okay, and then it will be in standard form. And then just a note on this one. You can also use separation of variables. Right, because if we just take the y over to the other side, we end up with y prime sine x is equal to y. Okay, so we end up with that. Can you see the pink? Is that, you can see it. Okay. So we have that. So we're going to have dy over y is equal to 1 over sine x dx. Right, you can do the separation and solve it like that. Okay. So for number 3, try it both ways. So try using the integrating factor, see what you get, and then try this way here, where I did the separation, see what you get. You should get the same thing for both. Okay, and like always, if you do 2 methods in the quizzes or test or exam, you'll get the marks for both. Okay, so if this was out of 5, you would get 10 out of 5 if you do both ways. Okay, same goes for the other methods, right? You do multiple ways, you'll get the marks for both. All right, any questions about the homework? Okay, and again, just make sure that these are in standard form. So 2 is in standard form, 3 is not, and 1 is not. So make sure it's in standard form first, and then solve. Okay, any questions on this? Okay, in the next lecture, we'll go through a quick revision of the Laplace transform. Then we'll look at solving these using the Laplace transform. And then after that, we will do mixed problems. So far, I told you what to use for each problem. When we get to the mixed problems, I will not say. Okay, so I'll just say, here's the problem. We can do it this way, right? It will be up to you to figure out how you get from looking at the problem to finding the method to solve it. Okay, so that will be in the next double on Thursday.